Hello, my name is Caleb Sytsma, and I'm currently starting my second year as a master's student in UGA's Warnell School of Forestry and Natural Resources under the direction of Dr. Rhett Jackson. My thesis project is part of a partnership with the National Park Service's Southeast Coast Inventory and Monitoring Network, which is led by Mr. Brian Gregory here in Athens. Today, I'll be presenting an overview of our project, which is on the effects of parklands on water quality of Metro-Atlantic streams with urbanized headwaters. While the project will also go into how urbanization impacts nitrogen and carbon levels in our study sites, the main question for today is how are urban streams' temperatures affected by flowing through national parklands? To answer this question, we have to back up a little bit and talk about how urbanization impacts streams. In short, we can say that watershed urbanization is bad for stream quality. This is because as impervious land cover increases in conjunction with urbanization, we see peak stream flows increase, which leads to steeper and wider banks as erosion increases in turn. We also see base flows decrease as precipitation never gets a chance to infiltrate downward and provide steady additions to channels. While these two effects on their own can cause havoc for aquatic biota that are accustomed to a particular flow regime, urbanization also tends to increase stream chemical, nutrient, and thermal loads by funneling water over hot, polluted asphalt and into concrete channels that give the water no time to cool down or drop sediments. In some cases, urbanization may completely move a stream into man-made concrete channels that have varying level of sun exposure, but the streams we'll be talking about today are largely still in their fairly natural channels. All told, these effects negatively impact a stream's overall quality, and they're considered symptoms of what Walsh et al. Called urban stream syndrome. This is important to talk about because we can't expect urbanization to simply halt. From 2001 to 2011, Cobb County, Georgia saw a 10% increase in urban land cover, which corresponded to a 10% increase in average runoff depth. Per Georgia's own data, our population is expected to rise by 44% over the next 45 years, with just shy of 40% of the total population being in the 5 largest counties in the state, all of which are in the Metro Atlanta area. Van Metre et al. Modeled the effects of climate change and urbanization with these trends in population and urban land cover expansion, and found that the extent of ecologically impaired streams will likely quadruple across the southeastern United States by the year 2060. These problems need resilient solutions, and we can look to decades of research on the impacts of clear-cutting and agriculture to find one potential method. It's widely recognized that leaving a wide strip of untouched land, known as a riparian buffer, on both banks of a stream can significantly decrease thermal and nutrient loading into streams, as doing so provides direct shading, allochthonous carbon inputs, and an opportunity for runoff to slow down, drop sediments, and spend at least a little bit of time moving via shallow subsurface flow. These effects hold true in urban environments as well, and Trimmel et al. Found that riparian buffers may be able to decrease forecasted temperature increases by 1 to 2 degrees Celsius. So that's a 1 to 2 degrees Celsius mitigation of a forecasted 4 degrees Celsius increase. We also know that the width of a riparian buffer can have an impact on its effectiveness, and that stream quality can shift as it flows from an urban environment to a suburban environment. However, I, at least, have been unable to find studies that examine the effects of flowing through a protected forested area has on the quality of a stream that begins in an urbanized environment, and this study provides a unique opportunity to do so. Chattahoochee River National Recreation Area and Kennesaw Mountain National Battlefield Park are 2 National Park Service managed areas in Cobb County, Georgia, and both are located downstream of some fairly heavy urbanization. These parks have been the subject of an ongoing project on wadable stream monitoring, and they both contain multiple streams that begin in urbanized areas before flowing into park administrative boundaries. As such, they work great for a study of this kind. For this study, we chose 3 streams in Chattahoochee River National Recreation Area, which I'll simply refer to as Chat from here on out. The furthest northeastern stream in this park is Mulberry Creek, shown right up here, which begins as a retention pond next to Hyde Farm before flowing through a forested area and eventually joining with a slightly smaller tributary before entering the park. Both it and the next stream, Beaver Creek, have watershed areas of approximately 200 hectares that are predominantly filled with open or low-developed areas. Beaver Creek begins in a residential area before flowing down into the park. Finally, Gunby Creek's watershed is approximately half the size of Mulberry and Beaver Creeks, but it also has a significantly higher amount of medium to high developed land. Along each of these streams, you can see black points representing sites we place temperature loggers at. It's also worth noting that this stretch of the Chattahoochee River is designated as a secondary trout stream because of the artificially low temperature waters coming out of Lake Lanier just a little bit upstream of here. So these streams are fairly small and rocky, and baseflow for all three is approximately 1 cubic foot per second, give or take a little bit. You can see from these highly degraded channel banks that urbanization and a legacy of agriculture have degraded these streams' overall quality. We also have 2 streams in Kennesaw Mountain National Battlefield Park, which I'll call KEMO from here on out. The northern watershed is Noses Creek, which begins in a heavily developed area just north of downtown Marietta before flowing through residential areas and then into the park. From there, Noses Creek passes out of the park boundaries and joins with Sweetwater Creek and eventually the Chattahoochee River. Ward Creek, the southern watershed, drains the western half of downtown Marietta before passing into some residential and forested areas, and it passes through a long open conservation easement, shown right here, before entering the park administrative boundaries. There's a beaver dam almost immediately downstream of the park boundary that leads to some interesting channel dynamics depending on how recently it rained. After leaving the park, Ward Creek eventually converges with Noses Creek before joining Sweetwater Creek and the Chattahoochee. These watersheds are much larger than those of the Chat sites, coming in at around 1,200 hectares each. Their land cover percentages are essentially opposite of one another, with Noses Creek containing more forested land and Ward Creek containing more of the open to low developed land. Once again, the temperature loggers are the black dots along each stream. This map also shows the nitrogen sampling sites, which weren't shown for Chat because they're mostly the same as the temperature sites. They basically just overlap. So here I have a picture of each of the 2 KEMO streams. On the left here, you can see John Ward Creek, right at where that beaver dam I mentioned is. So the water slowly filters down through here and goes around each side of this large root ball. When there's enough precipitation, this actually ponds up fairly high and kind of goes back along a channel a little bit further upstream from here. That leads to it kind of diverting around this area, not all of the flow, but a small amount of it. And it goes down into a tributary that's otherwise stagnant. Here on the right, you see Noses Creek, which has several large boulders along its entire length. It also has a number of walking trails along it when it's within the actual park boundary. Overall, these are predominantly sandy and much less stony than the Chat sites. So we collected temperature data at a 20-minute interval from June to August in 2019 and 2020. In all, we placed 56 onset hobo temperature loggers at 26 sites along the 5 streams. We had a number of difficulties with this method, and over the course of 2 years of data collection, we lost 10 loggers to storms, theft, and data corruption. Furthermore, we didn't have any means of constant visual monitoring of the sites, but field visits showed that many loggers spent significant amounts of time dewatered during low flow periods. To remove periods where the recovered loggers recorded air temperature instead of water temperature, we filtered the raw data by hourly variation and precipitation data from the USGS gauge at Soap Creek. We then summarized the 20-minute intervals into daily data, which we summarized into weekly and seasonal statistics and filtered to remove serial correlations. So we ended up with serially uncorrelated daily statistics and some seasonal summary statistics. All hobo loggers were placed in PVC capsules to block sunlight while still allowing water flow, and these containers were planted in the streams either by epoxying them directly to large stones, shown right here, or by tying them to rebar stakes and pushing them down into the stream bed. Both methods led to some losses, as you can see in that left picture, as debris moved by storm events broke epoxy-affixed PVC off of stones and uprooted rebar poles. In some cases, even the permanent aquatic epoxy failed. So this actually wasn't a data loss because I had already recovered this logger. It's just to show that this can happen. This wasn't broken off by a stone. It just came loose at some point. I was just lucky enough to find it while I was out there collecting water samples. Following all of this, we finally had some data to start analyzing. These two figures show the summary of daily averages for each entire stream. So moving from left to right, we have Beaver Creek, Gunby Creek, and Mulberry Creek, all of those chat sites. Then we have Noses Creek and Ward Creek, the KEMO sites. Only every fourth daily average is included in these summaries to remove serial correlation between the sites. Overall, we see that Beaver Creek had the lowest temperatures on average and that Ward Creek had the highest. Mulberry, Gunby, and Noses Creek all stayed fairly similar across both years. If we go back and think about the watersheds for each of these streams, Beaver and Mulberry Creek should theoretically be around the same temperature, but that didn't prove to be the case. Similarly, Gunby Creek ended up being warmer than Beaver Creek despite its smaller watershed, and Noses Creek was not significantly higher than the Chat Creeks despite its much larger watershed. Going into each stream and looking at them site by site can help explain this. Along the x-axis of each of these figures, we have each temperature logging site in order from furthest upstream to furthest downstream. They're color-coded by their location, and a dotted horizontal line shows 22 degrees Celsius, the upper limit for many cold water aquatic biota. Mulberry Creek starts out very high at its furthest upstream point because the retention pond that feeds into it is almost completely unshaded for the majority of the day. From there, the temperature steadily decreases as it moves into forested land. When it enters the park, the temperature appears to stabilize. In Beaver Creek, we actually see a slight increase in temperature as we move down the stream, potentially suggesting that the temperature is rising due to increasing watershed size. Gunby Creek decreases somewhat as it moves out of its heavily urbanized headwaters and into the forested park, but the temperature quickly stabilizes and doesn't drop much overall. We also see that Ward Creek begins at a very high temperature as it moves out of the unshaded beaver pond and conservation easement. From there, it incorporates a slightly warm tributary, that one that's stagnant during low flows. It then cools off as it moves through the park and then stabilizes at around 24 degrees Celsius despite the inclusion of a slightly cooler tributary. Also, I apologize that my video cuts off a little bit of Ward Creek, but you can generally see what it's doing here. Logger loss in 2019 heavily affected Nose Creek, but all other streams have mostly the same results between the 2 years. Our 2020 data for Noses Creek shows that the temperature stays mostly constant through the park before increasing slightly at the furthest downstream point of our study area. Clearly, this tributary here is much lower than all of the others, but it's actually fairly far away from the main stem and doesn't necessarily give us a great picture of how those two parts of the stream are interacting. So, some current conclusions. We can say for certain that there's a site-based temperature variability, as both Ward and Mulberry Creek start out with unshaded ponds that lead to very high upstream temperatures. Noses and Gunby Creek also start at similar temperatures, which could be taken to indicate that Noses Creek's high amount of forested land decreases the impact of its large watershed size on its temperature, or that Gunby Creek's high percentage of medium to high developed land leads to a higher temperature than is normally seen in smaller watersheds like it. Or it could be that on both ends, the mechanisms I just described are kind of helping get the temperatures back, or not back, but get the temperatures closer to one another. Beaver Creek also appears to directly refute my hypothesis that moving through Parklands would decrease stream temperatures, as they in fact increase as they move from the subdivision into the park. We can also say that our streams overall follow the well-supported trend of water temperature increasing with watershed size. So right now this doesn't appear to be due to any particular land cover, because both our undeveloped and developed land covers increase at approximately the same slope with increasing watershed size. Finally, we currently suspect that we're not seeing the expected temperature differences between park and non-park sites because of Marietta and Kennesaw's fairly robust riparian buffer protections. Marietta's city ordinance is 7-10-050-A, and Kennesaw's city ordinance is 46-440, but they basically read the same way. All land development is required to leave a 50-foot buffer of undisturbed native vegetation on both sides of streams, and there's a further 25-foot restriction placed on impervious land cover. There are, of course, allowed variances and exceptions, but my analysis of Georgia's 6-inch aerial imagery along all 5 of these streams has shown that all of them are well forested along their entire reaches, with the exception of Ward Creek's conservation easement. Moving forward, I plan to conduct more analyses to try and separate out the influences of watershed size, land cover percentages, distance between sites, and canopy cover at each site and along the entire reaches to really try and figure out what's driving these temperature differences. We also plan to include Panola Mountain as a forested reference site. Finally, as of October of 2020, we had begun collecting water samples along these 5 streams to analyze how nitrogen and carbon concentrations fluctuate along the reaches. We're planning to conduct monthly samples until June of this year, 2021, and I'm particularly excited to see how that beaver dam and conservation easement impact the nitrogen and carbon in Ward Creek. So finally, I would like to thank several people for their help with this. So first is Dr. Jake Bateman McDonald, who started this project as a postdoc and has now become a professor at UNG. Mr. Brian Gregory again and the staff of the Southeast Coastal Network's Athens office have been consistently kind and helpful with anything that I've asked them for. Dr. Lori Sutter and the staff of the Whitehall Plant, Water, and Soils Lab are running my nutrient analyses. They've also helped me with developing my methodology and just generally getting all of my samples in and stored correctly. Dr. Sutter and Dr. Nanda Tagar are on my master's advising committee, so I'm very appreciative to them for all of the constructive criticism and just general guidance they've offered me. And finally, Miss Ann Couch and Mr. Anthony Winiger are my contacts at Chat and KEMO respectively, and they've just been very consistently kind and accommodating, and I very much appreciate both of them. So these are the major citations I used in this presentation. Obviously, there's more than just these papers that drove this concept, but these were the highlights. And at this point, I would normally ask for questions, but because of the unique format this year, I just wanted to thank you all for watching, and for those of you who are attending the GWRC, I very much look forward to your questions in a couple weeks. Have a great day, and thank you very much.